Hey guys, this is Hal L.R. Watkins back with another demonstration. This is related to my Dijkstra routing planning, which is Dijkstra is um, a algorithm for route planning. Uh, so, have you ever watched Google Maps or Waze pick the fastest way home in under a second? That same problem I solve here for a ride sharing app instead of a phone. In this video, I'll show in plain language how a virtual car in my simulator figured out the quickest route across a city map using a classic computer science method called Dijkstra algorithm. Um, no coding backgrounds required. I'll translate every technical term into something familiar as we go. The first file I have open is my map.csv. So basically, a road equals one line of text. Before a computer can find the fastest route, it needs a map, and this is the map pretty much. It looks like a plain list, but each line is one road. Uh, this line reads ABC. This line reads AB5. Read it like a sentence. There's a road from intersection A to intersection B, and it takes 5 minutes to drive, which you see here, AB5. The next line is BA5, which is the same road in reverse, which you see here. Going to my next file, which is graph.py. So graph equals map, node equals intersection, edge equals road, and weight equals travel time. So graph.py turns that list of rows into something the algorithm can search quickly. Computer scientists call the result a graph. Don't let the word pretty much intimidate you. A graph is just a map. Each intersection is a node. Each road connecting two intersections is an edge, and the travel time of the road is its weight. One rule matters here. Every every travel time is zero or positive. There's no such thing as a road that takes negative time. That rule is exactly what makes Dijkstra algorithm the right tool for this job. So my next file is pathfinder.py. And here we are going to focus on find shortest path function, which we have here. All right. So in simple terms, a priority queue um, equals a to-do list that keeps the nearest option on top. Instead of checking intersections in a random order, uh, hold on, let me just back up a moment. Yeah, let's focus on the Dijkstra algorithm, which always tries the closest unexplored stop next. Issues here. I got ahead of myself. Sorry. Okay. This is the heart of the project. Pathfinder.py and the function find shortest path. Um, so feed it a map, a starting intersection, and a destination, and it hands back the fastest route and how long it takes. Here's the plain language version. Imagine standing at an intersection A with a notepad. You write down the travel time to every intersection you can reach so far. Everywhere else starts out marked unknown. or in computer terms, infinity. In here, we imported heapq from graph input graph. Uh, so instead of checking intersections in a random order, the algorithm keeps a sorted to-do list called a priority queue built with Python heapq tool. Think of it as a stack or a sticky note that automatically reorders itself so the closest unvisited intersection is always on top. You're gonna go down to the while loop, which is here. The algorithm repeats one simple habit. Pull the closest intersection off the top of the list, then look at every row leaving it. For each neighbor, it asks one question. Is going this way now faster than any route already found to that neighbor? If yes, it updates its notes and adds that neighbor back onto the sorted list. It also keeps a second notebook, the predecessor dictionary, essentially breadcrumbs. Every time it finds a better route to an intersection, it writes down which intersection it came from. Once that destination is reached, it follows the breadcrumbs backwards to rebuild the whole route. And two parts of the map simply aren't connected. Sorry, if two parts of the map simply aren't connected, the function doesn't crash. It returns a clear no route result instead, an honest answer rather than a guess. Moving to so for scaling for Hughes maps, um, basically because of the sorted to-do list, this stays fast even if a map grows to thousands of intersections and rows. Computer science has written the efficiency as big O of V plus E log V. You don't need to memorize the formula, just know it means the approach scales well. Moving to car.py file, and we're gonna point to calculate route, which we have here. Basically, the car remembers its route instead of recalculating every time. So knowing how to calculate a route only only helps if a car can actually use it. That's what car.py adds. Every car object stores its current location and calculate route, hands that location a destination and the map to the function we just walked through. The result, the route, and the total travel time is saved directly onto the car. So once a car plans a trip, it remembers that plan instead of recalculating it from scratch every time the simulation is checked. Moving to test Dijkstra.py. This script is the proof, not just the promise. Um, this script proves the code actually works. It loads the save map.csv from earlier, creates a car parked at intersection A, and asks it to plan a trip to destination D. It also tests a map with two disconnected pieces to confirm the no route found. the no route found case behaves correctly instead of crashing. So we're gonna run this application. Just grab the terminal here and we run it. So here you're gonna see um, basically the fastest route from A to D. This is pretty much the answer. A to C, uh, A to C, C to D beats A to B, B to D, because 3 plus 1 is less than 5 plus 4. So the fastest way from A to D runs through C, not through B, because 3 plus 1 is 4 minutes, while the way through B would take 5 plus 4 or 9 minutes. Um, the car's own route and route time match exactly, confirming the whole chain map, algorithm, and car works together correctly. This is the same category of logic behind the X minutes away. A- Um, X minutes away estimate in real ride sharing apps. With route planning working, the next milestone can use it to automatically match the closest available car to a waiting rider. Thank you for watching.